So we just learned about how to measure distances to galaxies, how such measurements reveal the expansion of the universe. We also saw how the expansion rate indicates that an age for the universe is our own universe is about 14 billion years. And with that understanding, we now I feel we're ready to turn our attention back to the study of how galaxies form and evolve or develop in our expanding universe. Okay, so basically we are going to dive into trying to understand how galaxies form and evolve. And the first set of clues comes from deep images of the universe. Deep observations, and those are the Hubble ultra deep field, which you have seen before. We talked about it. Is that 1/3 the size of the moon, so a tiny region that looked pretty empty before the Hubble Space Telescope looked into and saw about a few tens of thousands of galaxies in here. Tens. All right. Okay, so now remember that we can use powerful telescopes, especially like Hubble Space Telescope. So like or as time machines. As in order to observe things that are far away, and because it takes time for light to travel from those very far away objects, that means the further we look into the universe, the further we can see back in time. And so when we look outward, we can see, as far as we can, the most distant galaxies that we observe have a look back time of about 13 billion years or more. So basically we're seeing really old light from young galaxies that is basically just formed, right? So these are deep, they're far away. Okay. Now the linkage between a galaxy's distance and its age gives us a remarkable ability. So now, simply by photographing galaxies at different distances, we can assemble some sort of family albums of galaxies in different stages of their development. Of their lives. So what do we have here? The time goes like this. It starts here. So this is basically Big Bang, or the beginning of the universe. Okay, so this is in years, and this would be today. And we take pictures of galaxies at different distances, right? And so it takes this many if the light takes this many years to actually travel from each of these galaxies, that means they are this many light years away from us, right? So these pictures especially the furthest galaxies, show how they looked like in their childhood, or basically reveal to us how the universe was in its childhood. And the pictures of so these are nearest to us, right? These show mature galaxies as they are today. Nearest right? These are barely put together, basically galaxies. So kind of like some of the first galaxies, and we reveal how the universe in its childhood. So another important note here is that we still can't actually directly observe the earliest galaxies. We need even more powerful telescopes than the Hubble Space Telescope, and that's why we're building more powerful ones, like, for example, the James Webb Space Telescope, JWST Space Telescope, which is scheduled to be launched in 2021. Scheduled to be launched in 2021. Pretty soon. All right. So we don't get to observe those galaxies in the very young universe, and because we're not we don't have that kind of information, we cannot see yet back to the birth of the galaxy, so we must use theoretical modeling. And here are some examples of how we believe the universe was very early after the Big Bang, where just kind of cropped a cubing region of the universe. And before we discuss about how this matter evolves, I wanted to mention that our best models for galaxy formation assume two things, kind of important. And one was that the matter, which is basically hydrogen and helium gas, filled all of space more or less uniformly when the universe was very young, say in the first million years after a few million years after its inception, after Big Bang, basically after its birth. And then the distribution of matter in the universe was actually not perfectly uniform, okay? It's almost uniformly distributed, but not perfectly uniform. And so what happened, then the gravity of the slightly denser regions are going to start pulling matter from the surroundings. And So these models show that the regions of enhanced density originally expanded along with the rest of the universe. However, the slightly greater pull of gravity in these regions gradually slowed their expansion, and within a few billion years, what I think it's happening, as the time passes, then the so-called proto-galactic clouds form in those densest regions, and this is where the very first galaxies are going to form, because it's within the expansion in those very dense regions actually halted. Okay, so this is where expansion of the universe halted, and the material within then begins to contract. Begins to contract and form the proto-galactic clouds. Basically, the clouds out of which galaxies like our own Milky Way started to form. Just as we suspect our own galaxy has been formed, so we believe many galaxies have formed from maybe even the mergers of multiple, a few of these proto-galactic clouds as well. And so what's going to happen next? So we have these, according to these models, the protogalactic clouds that eventually form spiral galaxies initially cooled as they contracted. Okay, so they cool down as they contract under gravity. Okay, and the first stars are going to get to be formed in the halos of these clouds, proto-galactic clouds. Now, these first generation stars were probably quite massive, therefore living and dying very fast within just a few million years, so a very short time compared to the time required for the collapse actually of the protogalactic cloud into a spiral disk, which will form thanks to the conservation of the angular momentum. So that's gonna happen with the leftover gas that was not trapped in those stars, and there is plenty of time for that gas to settle into that spinning disk. Okay, and so we end up with a disk population of stars that orbit the galactic center, kind of like this, in a fairly flat plane or a disk, right? And then you also end up with a spheroidal component. But remember, also in the halo of this disk as well. All right, where the stars have more randomly oriented orbits, right? Remember, they're kind of all over the place, right? And this spheroidal population consists of stars that were born before the galaxy's rotation before organized, which is why they have randomly oriented objects or orbits around the galactic center, while the disk population consists of stars that are born after the disk, right? So here stars are born after disk settles. Okay, and therefore they have similar orbits around the center of the galaxies. So basically pretty much what we learned about how a galaxy like our own formed. All right, so if this is what we think about how galaxies are put together, then why some galaxies end up looking so different, right? Like, for example, there are galaxies like M87, which is a giant elliptical galaxy. There is no disk component, right? While obviously for the spiral galaxies like NGC 4414, the disk is very prominent, and then there are prominent spiral arms and so on. So the question is, why do some galaxies end up looking so different? The thing is, we don't really have an answer, and we would very much like to tell the life story of each type of galaxies from the beginning to the end as completely as we told the life stories of stars. But there are so many aspects of galaxy evolution that remain mysterious. So I'm just gonna make this note. Galaxy evolution, or many aspects of galaxy evolution remain mysterious. Nevertheless, we are going to dive a little bit. We'll examine some of the ideas that at least generally outline galaxies' life story, and we actually have some promising ideas about why galaxies differ from one another, but that is in the next little lecture.